Gnanam Paramam Dheyam. Knowledge is supreme.
We are on our way to prove that finite field extension, if it is Galois, then it is simple. This is what we want to prove, and for this we are preparing, and we use the action of the Galois group of L over K on the field L, and we want to decide how do you compute minimal polynomial and characteristic polynomial of the arbitrary element of the field L. So, we are left with proving two equalities, and they are the following. So, let me just recall that part. So, theorem, what we want to prove, if L over K is finite Galois extension, and Y is an element in L, and G we are denoting the Galois group of L over K, then we want to prove one minimal polynomial of Y is the product x minus z, where z varies in the orbit of Y. This was one, and second was characteristic polynomial of Y is the product sigma in G x minus sigma Y. So, we want to prove this, and as I said last time also, it's more important to prove that the polynomials on the right hand side, they are a priori polynomials in Lx. So, this RHS of 1 and 2 are polynomials in Lx, but we want to prove they are actually in Lx, Kx. This is what is very important, because by definition the left hand sides are polynomials in Kx. So, this is what one has to prove, and then for proving one we need to prove that mu, this right hand side, is a minimal monic polynomial of Y. So, Y is the 0 of this, that is clear, because Y is in the orbit of Y. So, we need to prove that this polynomial is the minimal one, that means it is a polynomial of minimal degree, so that Y is the 0 of that polynomial. This is what we want to prove. It is clear that in 2 both polynomials have the same degree, because the extension is Galois. So, since L over K is Galois, cardinality of G equal to degree of the extension, and it is clear from this side that the cardinality of this product is running over all sigma. So, the cardinality is n, G, which is the dimension of this. So, at least the degrees are equal in this case. Okay, so let us prove one. So, proof 1. So, let me call f to be the polynomial on the right side. This is product z in gy, orbit of y, x minus z. So, what is clear? It is clear that the degree of f is cardinality of the orbit and f of y is 0 because y is in the orbit of y. Okay, so I want to first prove that the polynomial f is in. So to prove f has coefficients in k. So what do you have to prove? So I will prove that, so for arbitrary polynomial g in kx or Lx, and sigma element in the Galois group G, I want to define what is sigma G. Sigma G is by definition, you apply sigma to the coefficients of G. So if G is summation ai x power I is in from 0 to some m, these ai's are elements in L, then the sigma G is by definition summation I is from 0 to m sigma of ai x power I. It is applying to the coefficients. And to prove that f belongs to k, enough to prove. So to prove this, we will prove sigma of f equal to f for every sigma in G. Because if I prove this, let us prove this first. So to prove this, I have to apply sigma and see what it is. So what is sigma of f? So f we know. So sigma of f is applying sigma to the coefficients. But f is the product x minus z as z varies in the orbit. And then I have to apply sigma to this. But that means this is product z in gy, because sigma respects the multiplication. So this is same as the product will come out and x nothing to do with sigma. So x minus sigma z. But remember, if z is in the orbit, sigma z is also in the orbit. Not only that, therefore, orbit, so therefore this I could have just replace sigma. So this is same as this product is running over orbit of y. So I could have simply written this as sigma in G, sigma z in gy x minus z. But this is same as so this is same as f, because you apply okay, there is nothing much to say. So therefore sigma f is f. All right. So therefore all the coefficients of f are invariant under all the elements of G. So therefore all coefficients of f are fixed elements of the G operation. That is, they belong where? They belong to the fixed field of G. But this is K because we have proved that if L over K is Galois, then the fixed field is this. So that proves that, so this proves that the polynomial f this proves that polynomial f actually indeed a polynomial in Kx. Now we have noted that f of y is 0. Since f of y is 0, mu y must divide f. Where? In kx. Because mu y is a minimal polynomial of y and this f is arbitrary polynomial of y. So, arbitrary polynomial where, not arbitrary, one polynomial where y is 0. So, therefore, this f is in the kernel of the substitution map and kernel of the substitution map is generated by mu I. So, mu I has to divide f. Alright. But now, let us compare the degrees. So, therefore, degree of mu I is smaller or equal to degree of f. Remember, both are monic. F is also monic by definition of f. So, both are monic polynomial. One degree is smaller or equal to this. But now I want to prove that the degree of f is smaller or equal to degree of mu. I want to prove this. Once I prove this, their degrees will be equal and both are monic polynomial, one divides the other. So, that will imply mu equal to f. So, once I prove this, this will imply mu I equal to f, since both are monic. Since both are monic. So, I want to prove this. Alright. So, remember again our very important observation from Galois theory, that I want to prove therefore what? I want the degree of f. I know what is the degree of f. Degree of f is cardinality of the orbit, because f is the product of the linear factors which arise from the each element of the orbit. So, these degrees I know, and if I want to prove this, I should prove that this mu I has so many zeros. If there are so many zeros, then the degree of that polynomial will be at least that. So, I have to prove that we will prove that every element of the orbit gy is a zero of mu I. So, therefore, mu I will have at least the cardinality of orbit number of zeros. Therefore, the degree will be at least cardinality of orbit, and that will prove what we wanted to prove. So, take any element of the orbit. So, any element of the orbit will look like sigma y for some sigma in G. And now, what was our observation? I want to use my observation, namely, if I have an element and element of this Galois group. So, what is the observation? If sigma is an element in G and y was an element in L and y is a zero of mu I, then if I apply sigma to y, sigma of y is also 0 of mu I. So, that is very simple, because mu y is 0 and I apply sigma to this equation. When I apply sigma to this equation, sigma 0, which is 0, that is sigma of mu y, but sigma is an algebra homomorphism with respect the scalar multiplication, it respect the sum, and it respect the powers of y also. So, this is same as mu y of sigma of y. So, therefore, sigma of y is also 0. So, that shows this. This is the very important observation which is the crux of the Galois theory, and I will use it in n thousands of times. I will use this. Okay, so what did we check? We checked that sigma y is a 0 of mu I. That means whole orbit is contained in the 0 set of mu I. And that is in L. So, therefore, the cardinality, this polynomial is, so therefore, the cardinality of the orbit is smaller or equal to the degree of mu y. And that proves what we wanted to prove, and that finishes the proof that 1. So, I will just say this proves 1. Now, prove 2, it's about the characteristic polynomial. But that is very simple, because what do we want to prove? I want to prove chi of y equal to product sigma in G x minus sigma y. This is what I want to prove. First of all, what is the degree of the RHS? Degree of RHS equal to cardinality of the group G, which is the dimension of L over K, which is the degree of the field extension. And this chi y also has degree, because chi y is the characteristic polynomial of, this is a linear operator on L, and L is a vector K vector space of this dimension. So, therefore, this is also Lk. So, both have the same degree, both are monic. Yes. So, and therefore, well, there is a easy way also to conclude. So, both are monic, both have the same degree. And what do I know about chi y? Moreover, this is from linear algebra, what we observed. Chi of y has to be power of mu, some power of mu, because since mu y is prime polynomial, is a prime polynomial, in Kx, because it's a field extension. Now, therefore, what power? Here the degree of chi y is the degree of L over K, which is cardinality of G, because L over K is Galois, and this side is what? So, I want to know what can I write here, which power. So, that will be somebody here times degree of mu y, that is somebody, and degree of mu y I know, it is the cardinality of the orbit of y. So, what can I do here? There is no other choice than the index. So, therefore, what we observe is the degree of, so chi y has to be mu y power no, I said something wrong, the power cardinality of the isotropy. Box is, I want to write somebody here, but I know this is the index of the isotropy. So, how can I get the order of G? I have to supply here cardinality of Gy. So, here we have to write cardinality of G suffix y. So, we have proved this formula. Already we have proved that mu y is a product of this. So, now if you club one and you put it one and then you raise it to so many times, so that is now easy to check that. So, now check, I will just simply here check that from this implies chi y is RHS of 2, which is what we wanted to prove. And we know that we want to prove, so already I have indicated in the last lecture that this proves that, so 4 was, recall 4 was the degree of the field extension ky over k. Remember, k is here, ky is in between, and this is a subfield of L, and we want to know when can the equality happen, for which y this equality happen. So we are interested in the equality here. So when can that happen? So this we have noted, this is nothing but degree of the minimal polynomial of y. This is the definition, and this is clear. This is, we have observed this, and this is equal to cardinality of the orbit. So cardinality of the orbit is the index of the stabilizer. And when can equality happen? So this equal to L over K, which is, we know it is cardinality G, because this is L over K Galois. Therefore, when can equality happen here? When equality will be here. That means, so this is equivalent to saying this index should be 1. So gy index is 1 means gy is trivial. Not 1, index is the whole cardinality G. That means gy is trivial. So therefore, what if you want to prove that there is a primitive element, then we must show that there is an element in a Galois extension whose isotropy group is trivial. So that is what we want to prove. Alright, so this we will prove, but before we prove, I want to also define important concepts which is used for the future. Alright, so what, recall, I would say recall. Again from linear algebra. The two important invariants. So F is a linear operator on a finite dimensional vector space. V finite dimensional K vector space, and F is K linear. Then I told you, to this we have two polynomials, chi f and mu f. And mu f, the minimal polynomial, chi f is a characteristic polynomial, and this chi f divide this, not only divides, they have the same prime factors. This is the determinant of X identity matrix, n cross n identity matrix, minus the matrix A, which this matrix A we got it by choosing a basis, arbitrary basis, and n dimensional. Dimension of V is n. Now therefore, and this is a monic polynomial. So this polynomial looks like x power n plus a1 x power n minus 1 plus a0, where a0 an not a0 an a0 to a1 to an, they are elements of the field. It's a monic polynomial of degree n, and particular interest are these coefficients. As I said, this polynomial doesn't depend on the basis chosen. That is because determinant of two similar matrices are same, and if you change a basis, this A will change it to the similar matrix, and therefore one checks easily that this determinant doesn't depend on the basis chosen. So this is the characteristic polynomial of f, and all these coefficients are therefore very important. They are good invariants, and out of the two, the last one, that is the constant term of chi, and the coefficient of x power n are of particular importance. And what are they? They are therefore, so first of all this one, this is the up to a sign. So minus 1 power n an, this is nothing but the determinant of f. That is clear because I put x equal to 0. When I put x equal to 0, it is determinant of minus a. So that means minus, I have to get rid of minus how many times, as many as rows are there. So there are precisely n rows. So I multiply by minus 1 power n, and then that is the determinant. And what is a1? a1 is minus the trace of f. This is a trace of f. Trace is nothing but the sum of the diagonal entries. So that again does not depend on the basis chosen. So these are two very important invariants of the linear operator. Similarly, the remaining coefficients also have nice meaning like this, but that we do not need it here. So I do not, but they can also be described in terms of this matrix. They will in fact be up to a sign sum of products of r at a time elements of the, they are related with the minors of a, higher minors of a. These are only we are taking 1 by 1 minors, and here we are taking the full minor. So the definitions I want to make is the following. Now we have a field extension, finite field extension, and y is an element there, and we have this linear map now lambda y. This is a map from L to L, multiplication by L, any z going to yz. This is clearly K linear. It is not L linear, it is K linear. It is not a K algebra homomorphism also, because 1 does not go to 1. So it is only K linear map. That means this lambda y is an endomorphism of the vector space, not K algebra homomorphism. It is an endomorphism. So therefore it makes sense to talk about characteristic polynomial of lambda y, minimal polynomial of lambda y. But this is same thing as characteristic polynomial of y, and this is same thing as minimal polynomial of y. That is easy to check these equalities. So I would strongly recommend you to check this precisely. Check these equalities. Alright, once you check that, it is clear what is the norm of, so that is also called norm of f. So the norm of y is by definition determinant of lambda y. That is the norm of y. So it's to be more precise in the notation, norm of L over K of y. And trace of y is by definition again trace of this lambda y, L over K. And both these are elements in K. And now we will, in the next lecture, we will study more properties of this norm and trace. Here I would like to make only one comment, that these concepts are defined for arbitrary finite field extension. Arbitrary. I am not assuming the field extension is Galois, but I will use it to prove that the field extension, Galois field extension is simple. So we will continue after the break. So we still have to prove that Galois extensions are simple, and we are almost finish the proof in the next lecture. Thank you.